Welcome to Study Loop.
In this question, we are given that identical charges q, the magnitude is given, are placed at opposite corners of a square that has a length of 8 centimeters. So we have a square, and let's talk about its pictorial representation. So we have a square over here, and these are the vertices A, B, C, and D. Point A is one of the empty corners, so this is empty, and point B is at the center of the square. So let me just redo this. So A is at empty corner and B is at the center of the square, and the charge are placed on the opposite corners of a square. So this is charge Q and this is charge Q, and this one is point B. All right. So what we have to find now is a charge of Q naught. A charge of Q naught is placed at the point A and moves along the diagonal of the square at B. So what is the magnitude of the net electric force on Q naught when it is at point A? So there is another charge Q naught which is at A. So we have to find the net electric force on Q naught. So that's got to be that's got to be because of this Q and this Q, these two Qs. And since Q is positive and Q naught is negative, the force is going to be attractive in nature. So this force, let's say it's represented by F, it's over here, and the magnitude would be same for even this force since they are symmetrical. So that is F over here as well. So since these two angles are at 90 degrees, so the resultant force F net is got to be F root 2 or root 2F because they are at 90 degrees with respect to each other. So this is as per the vector addition property. Now the value of F is got to be K times Q naught over R square, where R is the length of the side, which is 8 centimeters. So we're going to write 0.08 whole square in meters. So let's substitute the values here. We have the value of K as 9 times 10 raised to 9. We have the value of Q as 5 times 10 raised to minus 6. We have the value of Q naught as magnitude is 3 times 10 raised to minus 6 over 0.08 square. So let me grab my calculator over here and do this calculation, do this work. So that's going to be equal to 9 root 2 times 5 times 3, 9 root 2 times 5 times 3, which is, and this should be divided by 0.08 square. So that's coming as 29831.06733 times 10 raised to uh, a minus 3 over 123. So this is going to be equal to 29.83 newtons. This is the net value of the force which acts on the Q naught at point A. Now it says that if sketch the placement of the charges, so that we have already done, and the direction of the net force, is got to be over here, and this will be at an angle of 45 degrees because they are at 90 degrees. And then it is asking that what is the magnitude of the net electric force when it is at B. Now Q naught has moved to the point B, so Q naught is over here. So what is the net force? So net force is definitely going to be zero because this is attractive over here. This is attractive over here. So the two forces which are equally and opposite to each other, that's definitely going to be cancelled out. So we will say that the F net at B it gotta be is gotta be zero. The next one is we talk about how much work does the electric force do on Q naught during its motion from A to B. So we have to find the net work done on the by the electric force in the motion. So we're going to use the formula that the work done is given by Q times the change in the potential. So what we are going to do is we'll say that the work done is going to be Q times the potential at B minus the potential at A. And Q is definitely Q naught because Q naught is moved. So it's Q naught. Now, what is the potential at B? At B or A, that's going to be because of these two charges. So since the potential is a scalar quantity, we can just add it. So at B, that's going to be Q over 4 pi epsilon naught R. So let's make a figure over here. At B, Let's find out due to just one charge. So we got to find this distance, which is half the diagonal. So for half the diagonal, we know that the diagonal is, if the length is given as 8 centimeters, so the diagonal is going to be 0.08 root 2, and this length is going to be half the diagonal, so that's going to be 0.08 root 2 over 2. And this is what we are going to use over here. So because of one charge, for the two charges that are going to be multiplied by 2, so that's going to be 2 times kq over this distance r. So this distance r is nothing but 0.08 over root 2 minus the potential at A. So the potential at A is again going to be 2 times the potential due to 1, that will be kq over r, uh, where r is this distance because the q is over here. So the r is going to be the length of the side only. So that's going to be 0.08. So let's substitute the values over here and get the answer. So we have kq is taken out. So we have kq q naught. In fact, 2k q naught. Then we have root 2 over 0.8, 0.08 minus 1 over 0.08. Let's put the values of so the q is 5 and this is minus 3. So that's going to be minus 2 times 9 times 10 raised to 9 times 5 times 3 times 10 raised to minus 6, and minus 6 will become minus 12 because this is given in microcoulomb. And this is root 2 minus 1 over 0.08. So the work done is actually coming in negative, and we'll find its value. Let me grab my calculator over here. So we have root 2 minus 1 over zero point zero 0.08 times 2 times 9 times 5 times 3. So this is coming as, it should be divided by 10 raised to minus 3. So that's coming as, the work done is coming as negative 1.4 joules up to 2 decimal places. So negative 1.4 joules is the required work done up to 2 decimal places. And is the work done positive or negative? So definitely that's negative. And when it goes from A to B, does Q naught moves to higher potential or lower potential? So definitely when it is going towards B, it is moving to a lower potential. That's because we can clearly see that since it's moving actually it's moving to a higher potential, because we can see that this is the potential at B. This is the potential at B, and not including the 2. Yes, we can include the 2 as well. So this is the position, this is the value at B, and this is the value at A. So clearly we can see that when we simplify it, we get this root 2 minus 1 over 0.08, which is a positive number. So it means that V at B is greater than the V at A. So it means that we are moving towards a region of the higher potential, because VB minus VA is positive, but it is because of the charge Q naught, which is negative, that the work done is coming as negative. So we're going to say that over here we can write that it is moving to a higher potential. Thank you.